the transaction abstraction is a simple and powerful way to protect shared data from inconsistencies. If a set of objects are shared by concurrent threads from the same processor or on multiple processors, then roughly speaking, the transaction abstraction protects them from inconsistency. The goal of this video is to highlight the inherent limitation of this abstraction and motivate a paper entitled Democratizing Transactional Programming and co-authored by Vincent Gramoli from Sydney and Rachid Guerraoui from EPFL. Let's consider the two following computations. T1 assigns x plus y to v and then y plus z to v prime. And T2 assigns some value alpha to x, some value beta to y, and some value gamma to z. If this executes concurrently, there will be a risk that the accesses to x, y, and z lead to inconsistency. The transaction abstraction enables these inconsistencies by using a simple keyword. For instance, by writing this, the programmer would stipulate that either T1 should appear to execute before T2 or the other way around. Basically, the situation where T2 executes between this first instruction and this one is precluded. This abstraction is simple and powerful because it reduces the difficult graduate level problem of concurrency into the undergrad problem of sequential computing. So here the programmer needs simply to stipulate the boundaries of the transaction and the rest is completely sequential. In fact, concurrency skills are hidden. So programmers can use the transaction construct to write concurrent programs, and behind the scenes skilled programmers would need to implement what we call the TM, transactional memory or monitor. And this is the piece of software or hardware that is supposed to guarantee that indeed this looks atomic. It is sometimes argued that the transaction abstraction is inefficient. Because of its simplicity, the transaction abstraction is inefficient or too restrictive. And this usually means that it reduces performance. But is that true? How can we know that precisely? One way to do that is to build two programs, P1 and P2, both seeking to implement the same higher level abstraction, one using transactions and the other one using something else. Say, for instance, the lock abstraction. So one could argue that the transaction abstraction is inefficient if P1 is somehow less efficient than P2. So one could implement both programs, measure their efficiencies to implement this abstraction, and then conclude that because P1 is less efficient than P2, then the transaction abstraction is too restrictive. But from a strict theoretical perspective, this might be wrong. Why? Because this could be simply an artifact of the usage of the transaction abstraction. One could use it in the wrong way, and which would lead to inefficiency. So proving that the transaction abstraction is inefficient or too restrictive simply by programming with it and comparing the program with the lock implementation of the same abstraction cannot be very satisfactory. So what I'm going to show here is that, in fact, theoretically speaking, there is an inherent limitation of the transaction abstraction, especially when compared, for example, to the lock abstraction. So the lock abstraction, roughly speaking, for those who don't know this concept, is a simple abstraction that enables to say, I would like to get exclusive access to a given variable. Roughly speaking, for the sake of this talk, for the sake of this video, this is enough. Let's go back to the two computations mentioned above. So assume we want to do this and then this. And assume that the consistency we would like to have is the following. We would like x and y. We would like exclusive access to x and y during this first computation. We would also like an exclusive access to y and z during this computation. But we would also want y to keep the same value across these two computations. So with locking, this is easy. I would say lock x, lock y, execute this computation, and then here I would also lock z. But I could unlock x here, because I don't need x to remain with this previous state in this computation. So I would lock x, lock y, unlock x, lock z, and at the end, unlock y and unlock z. So assume that this is the semantics that is required, and indeed this is something I can implement with locks. How could I implement this with transaction? With the transaction abstraction, there are basically two options. One of them is to do the following, is to encapsulate the entire computation, meaning the first one and the second one, inside the same transaction. But in this case, we will be restricting concurrency too much. Why? Because as expressed here, we don't need to keep X locked in this second part of the computation. This will be too strong, and we will be restricting concurrency. So this is option 1. Option 2 would consist in doing the following. Atomic here, and then stopping here, and then starting again here, and finishing here. So here we would be executing the assignment of x plus y to v, and here we'll be executing the assignment of y plus z to v prime. But again, this is not exactly what we want, because what we want is to be able to say that y remains the same across these two computations. If we close the transaction here and open another one here, nothing prevents another transaction from accessing y. So this would be too weak. This paper in CACM elaborates on this inherent limitation of the transaction concept and show how to circumvent the actual limitation by enabling different kinds of programmers to express different kinds of the semantics within the same concurrent program. Hence the term democratization.